So I had no idea whatsoever what this round table was about. I kept asking and nobody else seemed to know what it was about. So what I'm going to do is I'm going to make a couple of brief comments. One about, these aren't joint, they're two separate comments, if you will. One about black holes and black hole entropy or temperature, and in particular the importance of analogies and how one can use analogies, which I think has some philosophical content in it. And the other, some questions that have come up in my mind, both in hearing the talks here and in stuff that I thought about before, about cosmology and some of the issues there. So black holes has been a very long subject. I certainly have been trying to understand what goes on with black holes, and in particular what goes on with the evaporation of black holes since the early 70s. One of the amazing things about physics that we've discovered in this century is that physics seems to describe the world in all of its aspects with an amazingly small backpack full of ideas. The harmonic oscillator just keeps reappearing everywhere, all of the time, in all kinds of situations. For black holes, the discovery of black hole thermodynamics, all of that stuff that Bob Wall told us about, all rests on that discovery that Hawking made of the temperature. And as Bob emphasized, it's really weird, because that temperature is a statistical temperature in the sense that one looks at the distribution of the particles, the distribution of energy coming out of the black hole, the statistical distribution, and derives the temperature from that. And yet it doesn't arise out of any kind of statistics. It's quantum field theory propagating in its absolutely simplest manner in this background space-time that produces this thermal distribution. So in trying to understand something like anything in physics, very often analogies are useful. And analogies are usually thought of as being most useful when the analogy is best. But as I'm going to discuss, it turns out that analogies are even useful in places where the analogy fails. And the analogy that I came up with through a whole long history was the analogy between black holes and a moving fluid. Let's go back to Hawking's derivation. One of the key questions there is that the derivation just doesn't look right. Why doesn't it look right? If we take I don't even have a curve. Oh, there we have. If we take the radiation emitted late in the black hole and ask where did that quantum radiation come from, the answer is, well, you just simply propagate it back into the past. And since we're just doing linear quantum field theory, that's incredibly easy to do. The problem is that the answer is absurd, because this radiation can't come from inside the black hole. It comes and it gets closer and closer to the horizon and squeezes up against the horizon exponentially fast, and finally escapes at the point at which the black hole is formed. That exponential squeezing is such that for a solar mass black hole, at 1 second, the radiation emitted at 1 second comes from fluctuations in the vacuum of frequency e to the 10 to the 5th. No units. If I measure it in units of the mass of the universe divided by h bar, I still get that same e to the 10 to the 5th. Obviously, the theory is completely silly at that point. Well, what's the analogy? The analogy is a fluid analogy. One imagines a waterfall in which the water travels faster than the velocity of sound at a certain point. At this point here, at that point, the sound can't get out, and it acts exactly like the horizon of a black hole. Furthermore, that system acts exactly like a black hole because one can take Hawking's argument line by line, apply it, and get a temperature coming out. Of course, this e to the 10 to the 5th doesn't occur there because once the wavelength becomes shorter than the interatomic spacing, one doesn't have sound waves anymore. And so one gets a natural cutoff there. The other nice thing about this is that one can do experiments. And here's a sketch. I love this sketch because it looks like a sketch from a 19th century physics textbook of water flowing in a flume over an obstacle. That obstacle produces horizons, a black hole and a white hole horizon. A white hole is just the time inverse of the black hole. One can send waves out in it, and one can measure the Bogoliubov coefficients by measuring the height of the water. This is a laser shone on the water. The water is filled with a dye, which fluoresces. The mean free path in the water is much less than a millimeter, so one can measure the surface of the water to within about 100 microns and determine the waves traveling in the water. This is a nice example. The crests give us the phase velocity. The center of that packet gives us the group velocity. So we notice that over here, we have, just at this side, we have a horizon. Namely, the wave packet can't get into that region, even though the phase lines do get into that region. So the phase velocity, that's not a horizon for the phase velocity, but is for the group velocity. One can do the Fourier transform. One gets curves like this. The stuff on the right is what's usually called the positive frequency part of the Bogoliubov transformation. The stuff on the left is the negative frequency part. The stuff in the middle is the incoming wave, whose wavelength is far too large to be resolved. When one looks at the ratio of the positive to negative frequency, one gets this very nice straight line, which tells us that there's a temperature. These Bogoliubov coefficients directly translate into a temperature. Unfortunately, one can't see the quantum fluctuations because that temperature is 10 to the minus 12 Kelvin, and Vancouver's water is a little bit warmer than that. Okay, this is a nice analogy. It shows that Hawking's arguments work for this water. But one of the questions is the analogy also breaks down. And it's in fact in the breakdown that in fact most of the interesting part comes. So we get support for Hawking's arguments both from theory and experiment for this water, but it's exactly in the place where the analogy starts to break down, namely the fact that on short wavelengths the system doesn't look at all like quantum fields in a curved spacetime, that one gets the most interesting stuff because this system is thermal, despite the fact that the theory is totally different at high frequencies. That tells us that the effect is incredibly robust. It really has nothing to do with high frequency physics, as Hawking's derivation might lead one to believe. It's a low frequency, long wavelength phenomenon. And that's what one can gain out of the differences between these two analogies. So analogies can be powerful not only just in those areas in which they're similar, but also in areas in which the two systems differ, and they can teach you about the one system precisely because of the differences between the analogies in the two areas. So that's the one thing that I wanted to talk about. The other one is to raise an issue. It's something that I sort of raised back about over 30 years ago by now. And that is one of the peculiar features of cosmology from most other physics is everything is in some sense backwards because our observations are all being made after the system that one is trying to describe, namely, how does the early universe behave? Even though all of our physical theories, one tries to one talks about, the theory plus initial conditions, and one tries to derive the initial conditions from the observations that we make now. That has two problems in cosmology. One is that in classical physics, we know that initial and final conditions are equivalent. One can always use the equations of motion to map final conditions onto initial conditions. But the problem here is that the system is unstable. So that as I propagate things backwards, what were the dying modes in the usual terminology in cosmology become growing modes, i.e. instabilities. So that one has the problem that if one specifies the final conditions, tries to determine what the initial conditions were, the whole thing just you've got the initial condition problem that one has to specify the final condition to arbitrarily high, exponentially high accuracy in order to figure out what those initial conditions are. But it gets worse when one tries to do quantum cosmology, because in quantum mechanics, final conditions are no longer equivalent to initial conditions. And this is my favorite example. Let's say at 9 o'clock, I have a spin 1/2 particle. I measure sigma x to be 1. That's the Pauli matrix, which has eigenvalues plus and minus 1. At 11 o'clock, I measure sigma y to be 1. So I've got initial conditions. I also have final conditions. And I now ask, what's the probability if I measure sigma theta, cos theta sigma x plus sine theta sigma y at 10 o'clock? Well, I've got to be careful. I can't measure it too accurately, but you can use the whole idea of weak measurements that Aharonov developed in order to not to disturb the system too much in the middle. But the answer is that sigma theta in the in-between time has probabilities that look like this funny curve. Namely, the probability is 1 that if I measure sigma x, I'm going to find the value 1. The probability is 1 that if I measure sigma y, I'm going to find the value 1. Between those, it dips a little bit, and then the probability goes down to 0 for sigma x minus 1 and for sigma y minus 1. There's no wave function that gives us that probability distribution. There's no density matrix that gives us that probability distribution. Quantum mechanics, however, very simply, I did this calculation, gives us that answer. So to answer Shelley's statement, in some cases, the wave function is just completely irrelevant as far as the theory is concerned. Never mind trying to classify what kind of a wave function one has. The problem in cosmology, then, is that when one tries to retrodict from the observations we make now, both classically and quantum mechanically, one tends to run into bad singularities. One tends to think that one can think of the system as, well, we've got some conditions set at the Big Bang or something, or before inflation, and what we're going to do now is to look at them. Well, almost everything we do now, when we try to retrodict it, ends up in the universe having a singularity before before going backwards in time, one gets to the place where one wanted to specify the initial conditions. So given one's favorite theory of inflation, it's virtually impossible to make measurements now which, when they were retrodicted, would not run into super Planck scale physics, i.e. singularities, long before you got to that initial surface, that initial hypersurface slice. Now, many of us, we've heard a number of talks which I think have had the same kinds of concerns. Hartle, Page, and various other people here have talked about it. What are the implications of observers? I think this is constantly trying to not take seriously this fact that the observations are now and the initial conditions were then, and is constantly trying to think about the universe as if it were a standard initial value problem where we can set up a wave function at an early stage and then propagate it forward and ask questions about it later. One small comment on Jim's when he talked about Bohr and his division of the world between classical and quantum. It sort of reminded me a little bit about Alfric's comments when he was asked to translate the Old Testament. And he said, the work of translation is very dangerous to me or anyone to undertake because I fear that if someone foolishly reads this book or hears it read, that someone might wish to think that one should now live under the new law just as if the old fathers, etc., etc. Translation is dangerous because people take it literally. What he calls foolish people will take things literally. And of course, we see that all over the place with the sort of fundamentalist, Tea Party kind of people who will take everything that's written, for example, in the Bible literally, whereas Alfric and others realize that very often one has to read it metaphorically. And sometimes I believe we do the same thing with Bohr, where what he is trying to give is a sort of a metaphor. You know, remember he was the one that always said one should never speak more clearly than one thinks. And I think he did that, and what tends to happen is one then takes his words and interprets them as though they were written by Russell or Whitehead in their work on logic. And I don't think one can do that. Physics is a human endeavor, not an endeavor of God. We're trying to understand the world in terms of our own knowledge and our interactions with the world. And one has to ask how one can embed this knowledge and these interactions into the theory. Copenhagen, which I think is more Heisenberg than Bohr, as Don Howard emphasizes, but anyway, Bohr's interpretation is his grappling with this problem as to how one embeds our observations into the theory. And I think we've heard other people trying to do the same thing. I could make comments about quantum nonlinearities as well. Most of cosmology nowadays is under the assumption that all of cosmology can be done linearly. Okay, all of cosmology can be done linearly. It has some basis, but even Linde has pointed out that in his eternal inflation, that there's a problem that the nonlinear large-scale fluctuations produce different universes. Those different universes then interact back on the expansion rate and on the quantum fluctuations at the small scale and alter the universe at the small scale. But I'm just being told that I have no time, so let me quit. Thank you.
Eric.
So I was just invited to this conference about 6 days ago. So I haven't had much time to prepare anything, and in fact, I was in the same boat as Bill. I wasn't sure exactly what the roundtable, what format this was supposed to take. So I'm going to restrict, but Simon did, when he invited me, he did specifically say that he would like me to say a few things about some recent arguments I've made about the character of black hole mechanics in the purely classical setting. So I will say a few things about that, say a few things about the problems that Bob Wald has been vigorously telling me that my arguments have, and perhaps try and say a few things in response that Bob will hate. But I also, before I do that, since I take it that part of the point of the round table is to motivate discussion of the talks that have already been given, I also would like to raise a few questions about general questions that apply to several of the talks we've seen so far. So I'll begin by raising a question about, we've heard a lot of talk about probabilities in cosmology, and I have a very hard time making sense of talk of probability in cosmology for the following reason. if we take seriously the idea that, and so I guess I will follow tradition and say that I'm talking about cosmology with a small c here, or metacosmology, so I don't have to specify whether I'm using majuscules or minuscules. If we take seriously the idea that the universe could have been, in some sense or other, any reasonable solution to the Einstein field equation, that basically conforms to the finite limited set of observations we have, then we're talking about, and even if we just fix once and for all, let's say a differential manifold that we're going to consider as the underlying space-time manifold, then we're dealing with an infinite dimensional family of metrics over that manifold. In fact, it's an infinite dimensional Fauché space. But now the question is, questions of probability are usually posed in this context by asking about a measure, the existence of a measure. But the kinds of questions people like to ask or pose when they're talking about probability, and this has come up over and over in several talks, are questions about typicality and genericity. But what does it mean for something to be typical? Well, it means that I have a set of things. What's typical in that set? Well, something's typical if most of the things are like this right here. So that's what I mean by typical. Most like this. Most are similar to this. Well, most is a measure theoretic notion. Like this, similar to, is a topological notion. The only way I know how to make sense of similarity in this context is topologically. But, I'm sorry?
Why not metrically as well?
Sure, no problem. But even if I do metrically, that's not going to help me, because it's a well-known theorem that there is no well-behaved Borel measure on infinite dimensional Fauché space, no non-trivial Borel measure on infinite dimensional Fauché space. So if I want to have a measure that respects the topology or the metrical structure on the space, at least the locally convex structure on the space, in a way that I can make sense of talk of similarity and genericity, and have them conform, the only measure I have is the trivial one that assigns zero measure to every measurable set. So this is a serious question I have for people doing cosmology and talking about probability in cosmology. What do you mean? I really don't know, because just because the only way I know to think about these things is using nice Borel measures, and there's just not one. So that's first question. Second, a very quick remark about, in particular, about Brian's talk that just occurred before this, following up on Bob's question. So Brian, if you tell me that there's an infinite number of gravitational energies, I don't know why I should think of it as an energy if you can't tell me, for instance, how to use it to heat up my cup of coffee. And to put it a little more precisely, none of these mathematically conserved quantities you're talking about, they mediate no physical interaction. They couple to nothing else I think of as physical, like the Maxwell field. So what motivation do I have for thinking of them as energy? So general question, spiritual question, and now a few very quick remarks about classical black holes. How much time do I have?
About 10 minutes.
Okay. So Wald and Unruh argued very vigorously in their great 1982 paper on acceleration radiation that, in fact, one must take quantum mechanics into account in order to take black holes seriously as thermodynamical objects. And Bob gave a very beautiful presentation of that this morning, for his reasons for thinking that. And I guess for a while, I would never want to claim that quantum mechanics is irrelevant in thinking about the thermodynamics of black holes. But I've been curious for a while about the question of whether there's a way of trying to make sense of purely classical black holes with no input from quantum mechanics whatsoever, and still think of them as thermodynamical objects. Whether there's a way of thinking of the classical laws of black hole mechanics really as the laws of thermodynamics extended, of classical thermodynamics extended into the realm of black hole physics, of classical black hole physics. So I came up with, the standard argument that one can't do it is, as Bob mentioned, that one really should consider classical black holes as having temperature absolute zero. Well, why is that? Well, a very, very typical thought experiment you'll see in the literature on this is take a Kerr black hole, put it in a big reflecting box, fill the box with thermal radiation. Eventually all the radiation will be absorbed by the black hole. The black hole won't emit anything, so perfect absorber, perfect non-emitter must have temperature absolute zero. But it occurred to me that isn't necessarily a very good argument, because in fact the black hole does emit stuff. It emits gravitational radiation as the thermal radiation falls in. And if we're trying to think about black holes as thermodynamical objects, as having associated entropy, a real classical thermodynamical entropy, and we want to try and make sense of the idea of a thermal coupling. What does it mean for a classical black hole to thermally couple to let's say, an ordinary thermodynamical object? Well, then surely the appropriate notion of energy to use in this case is non-localizable, ordinary non-localizable gravitational energy, the kind that you find in gravitational radiation, for instance, or the kind that you find that mediates monopole coupling, say, of the small box being lowered towards the Schwarzschild black hole. So based on that idea, I constructed the analog of a Carnot cycle for that essentially that uses an ordinary classical thermodynamical system, and one of the heat sink of which is a Schwarzschild black hole. And is running through actually fairly standard the arguments you'll find in Sommerfeld's textbook or Fermi's textbook. It actually falls out, and assuming the first law of black hole mechanics, it actually falls out very, very neatly that surface gravity ends up playing the role of integrating factor for the heat you dump into the black hole. So that looks a lot like temperature. And what you get when you use temperature as when you use the surface gravity as the integrating factor for the heat you dump into the black hole, the quantity you get, the associated quantity is the area of the black hole. So it looks all like entropy. And my thinking was, well, if we're using a black hole to couple the ordinary thermodynamical systems in the completely standard way that we do in ordinary classical thermodynamics, and surface gravity plays in this Carnot cycle the physical role of a temperature, and the area is playing the physical role of an entropy, what more can we ask? We really should think of them as thermodynamical temperature and entropy. And I just wanted, of course, to stop there and say, great, I solved the problem. But Bob has been pushing me because Bob thinks that I still haven't resolved the issue that without taking quantum mechanics into account, and for instance the acceleration radiation, the buoyancy effect that you get when lowering the box, that one will be able to affect arbitrarily large and systematic violations of the second law. So, again, the way that he suggested, if I lower the box that's filled with matter exactly to the event horizon, and while I'm doing that, I lift a weight at infinity. So I'm extracting basically the stress energy of the box as I lower it. So I can arrange it so that right as it hits the event horizon, the box has zero stress energy. But I've done it all adiabatically, so there's still all the entropy in the box, of the stuff in the box. I open the box, dump it in. Area of black hole isn't going to change because the mass isn't changing, but I've lost the entropy. The entropy has vanished in the outside world of what was in the box. So that looks like, and I can just do that over and over and over again. So I can turn heat into work with 100% efficiency. So it looks like, unless I say the temperature of the black hole is absolute zero, I'm going to get violations of the second law. Or another way of saying it is, in fact, the only sensible thing to say is well, I guess I'll just leave it at that. You get systematic violations of the second law. And so I've been playing this game with Bob for the past couple of days, trying to come up with ways to argue that, well, just basically trying to get out of the problem. And so at first I said, well, you know, look, you're going to have to make arbitrarily precise measurements to do this. You know, because you have to, first of all, you have to have with arbitrary precision, know exactly where the event horizon is. And with arbitrary precision, know that when you lower the box, you're right at the event horizon when you open the box, otherwise this isn't going to work. And so that sounded a little bit to me like a Maxwell-Demon kind of problem. You know, if I can do things with arbitrary precision, then sure, of course I can violate the second law. And so the problem didn't seem to me to be any more severe than it was in ordinary thermodynamics. But Bob, I think, rightly pointed out that this really isn't like the Maxwell-Demon case, because one of the reasons why people don't worry about Maxwell-Demons, at least many people, is the idea that the Maxwell-Demon itself has associated entropy, and after the Maxwell-Demon thermalizes, it won't be able to function for arbitrarily long periods of time. But it doesn't, and in this example, you don't have any mechanism that has that flavor. So then I thought, well, okay, fine, but look, there's tension in the rope, and the way the tension in the rope operates, it's kind of like it's acting as an effective momentum flux. Because the stuff in the rope, every bit of the rope is pulling on each other, and so that you can't, in fact, lower the box. Even if you assume the rope is massless, which you always do in this idealization, there's still, as you lower the box and as it gets closer and closer to the black hole, the tension increases arbitrarily, to arbitrarily large amount. And so you have to take account of that stress energy. And so it's actually impossible to, so you won't, in fact, be able to extract all of the stress energy in the box originally into work at infinity, because part of it's going into the tension that's holding the rope together. And Bob didn't like that either, but, because he said, well, look, it now looks like you're changing the rules of the game, because I can, let's just say I have a rope that doesn't satisfy the dominant energy condition, and then I can get around that too. So I think where I stand now is that I am definitely worried about Bob's challenges, but I'm still not completely convinced he's right. So I'll leave it there. You want to get a chair? And
Yeah, well, why don't you have this one? Okay, so right, I've seen about 4 questions already, so let's start with Tom Banks.
Thank you. Bill, in the dumb hole analogy,
Right.
the hole has some entropy. There's certainly no sense, I believe, that entropy comes from the phonons,
Right.
right? The entropy comes from the microscopic degrees of freedom in the water.
So remember, in the black hole, the way the argument goes is that you get a temperature. The temperature is proportional to is a function of the energy. As soon as the temperature is a function of the energy, you can then plug it into, TdS equals dE, integrate that up and get an entropy. In the black hole, in the dumb hole case, the temperature is proportional to the velocity of the fluid, the rate of change of velocity of the fluid, which has got nothing to do with the energy of the system.
I see.
So, there's no sense in which you get any kind of entropic consequences of it, which makes the black hole case even more of a miracle than it seemed before, because one is getting exactly the same arguments, giving you a temperature here as you got there. It's the foundation in both cases of this sort of thermodynamic behavior of these systems, and yet the two systems behave in such a different way in that case, which is, just as the existence of the temperature seems to be incredibly robust to what kind of system one looks at, the existence of the entropy seems to be incredibly non-robust to what kind of systems one's looking at, and makes the existence of the entropy in the case of the black hole even more mysterious than it was before, to me at least.
So I've got about 5 people in the queue at the moment. I've added 2 more.
Hi, David Albert. A comment for Bill. The results you quoted about statistics of pre- and post-selected ensembles, I mean, it's not only the case that those are consistent with assigning a unique wave function to the world at every time. That's how you derive them. I mean, you spoke about, deriving these things from ordinary quantum mechanics. Indeed, you do. And in all of the sort of solutions to the measurement problem, which assign a unique quantum state to the world at any time, Bohm's theory or Everett or GRW, you derive exactly these results in all of those theories. Once again, it's not only that these results are consistent with assigning a unique wave function to the world at any time. You use a unique assignment evolving through these measurements in order to derive these pre- and post-selected results.
No,
so I don't think there's any tension at all between
as
those results and describing the situation of the world at any time with a unique wave function.
As we know, as Haranov, Bergman, and Leibovitz showed, you can also derive them by going backwards, and you get a totally different wave function for the world going backwards that you did going forward.
No, yeah, that corresponds to...
Which of those are you supposed to? Or,
No, this just corresponds to...
Or in Haranov's, current view, you get one wave function traveling back from the future, one wave function traveling forward from the past. Which one of those is now supposed to be the wave function for the world?
So look, there's
what the wave function, what I would say is that the wave functions are one way of setting conditions on the theory. The theory is, as usual, generic, describes many, many different possibilities. The wave function is the way of making it apply to a particular situation. But quantum mechanics, unlike classical mechanics, you cannot ascribe that to an initial condition. And there are certain situations, questions that you ask of conditional questions you ask of the theory, in which the wave function is simply an inappropriate vehicle to ask those questions.
No, I don't think any of that is true, but we can discuss it later. I don't want to drag it on right now.
I had Eric Winsberg. Where's he got to?
Thanks. Yeah, Eric Winsberg. So I had just a sort of a methodological question about the dumb hole stuff. So if I understand it right, you have these 2 derivations, which are the derivations are identical, and they both have the same property that you think they fail. In the one case, they both have these very high frequency modes. In the one case, you think that's got to fail because it's going to the Planck scale. And you think the approximation of treating it as
super Planck
super Planck scale, right? And in the other case, you think it fails because it's going to the intermolecular scale, and treating it as a fluid is a bad approximation there. Okay. So what I'm trying to understand then, I'd like to just hear you say more about what kind of reason you have to employ, what kind of inference you have to make to get from. Suppose you observe everything you'd like to observe in the fluid. Suppose you've even found the quantum correlations, everything. And you say, okay, even though I think the derivation here is kind of fishy, the conclusion is true anyway.
Well, in the dumb hole case, you can actually take into account these deviations due to the atomicity of matter.
Right, because you know the atomic theory of fluids.
We know the atomic, and the primary effect of those is to change the dispersion relationship, and you can go ahead and carry out the calculation with an altered dispersion relationship, and you find you still get exactly the same temperature as you would have in that hydrodynamic approximation.
Okay, so what's the crucial move then to say, therefore the same thing follows in the black hole case, when there we have no idea what the sort of intermolecular right? I mean, I'm just trying to get...
Well, The move is basically that you have the same derivation and the same behavior at low frequencies, okay? You have the same result in both cases. In one case, the result is independent of the behavior of the high frequency theories. Therefore, one suspects, although this certainly isn't proof, that no matter what kind of changes one is going to have in the high frequency behavior in the black hole case, and there has to be, because obviously a quantum fluctuation whose mass is, 10 to the fifth, e to the 10 to the fifth times the mass of the whole universe, is not going to obey the same equations as a free quantum field. That in that case as well, one is going to get a similar robustness. And it suggests very strongly that the actual reason for this thermal emission is not something to do with high frequency physics, but has something to do with this low frequency behavior of the theory near the horizons of the black hole. Notice that in the sonic case, one doesn't even, because of the altered dispersion relationship, one doesn't even have horizons in the traditional sense. Stuff can come from the inside, or a different dispersion relation can come from the outside. At high frequencies, the horizon is at a totally different place, and yet you still keep getting the same result.
Okay, I've got Bob Wald, Jim Hartle, and Simon Saunders who've been waiting. I think I'll take those three
Sure.
in that order, and then we probably better break for lunch.
Okay.
Yeah, so actually, with regard to one of the things you said, Bill, I just wanted to make a comment about it. So in terms of inferences about the past from the present, I mean, where there's obvious difficulty, because if we take conditions here and go back in the past, we get instabilities and get, I mean, that was the point that you made. I mean, I just wanted to point out that sort of the second law of thermodynamics is playing, a big role in this, and one doesn't have to go to cosmology to see that. I mean, if you have an egg on the floor, if you try to look at the position and velocity of, the egg and figure out where it came from, you don't get very far. But if you make the hypothesis that the egg rolled off the counter, let's say, you can even parameterize that and maybe get beautiful fits to your parameters and really have some confidence that it actually rolled off with this velocity off this edge of the, and that's exactly what we're doing in cosmology, I claim. We're making simple.
Agreed. I mean, one then keeps trying to play this game of let's start at the beginning, let's track things forward and see whether we end up where we seem to be.
Yeah, exactly. That's the way we figure out what happened.
What I was trying to point out was that once you get quantum mechanics coming in there, it gets even more difficult to do that. Once I make a measurement now, if I now track that measurement back, I'm going to get, Planck scale kinds of fluctuations long before I get back to that initial surface on which I thought I wanted to set my initial conditions that brought me up to the future.
Yeah.
And that I think that makes the issue even more difficult.
Yeah, I agree. And then quickly, Eric, I can't resist.
Of course.
So I think, I mean, in order to avoid all these, ropes and, can you make ropes and boxes strong enough and so on, I think a much simpler thing to do would be, once you've assigned the finite temperature to this classical black hole, I'll just build a very big box with reflecting walls, and I'll put in radiation that's at a lower temperature than what you said, and I'm going and let it just evolve on its own, no ropes and so on. And of course, the black hole is eventually going to absorb the radiation, and you're effectively getting energy transfer from lower temperature to, from the lower temperature to the higher temperature. I mean, if you just put in the entropies, you'll get a violation of the second law, just with the assumption that eventually the black hole is going to absorb all the radiation.
Well, that's actually not clear to me, because the black hole has negative specific heat. So are you sure?
Black hole what?
The black hole has negative specific heat. So
Doesn't matter. It's still
are you
it's
sure?
going to eventually absorb everything in this box, classically.
But it's just not, it's not clear to me that the amount the area is going to grow will be less than the.
Yeah, okay, but I'm claiming that
yeah.
if you just one does the calculation of the initial entropy, given a gas with temperature lower than that of the black hole in a very big box, the initial energy and entropy of that gas versus the black hole, and then if the black hole ends up absorbing everything, it'll have an area increase associated with that, and you're just going to get a we can do that later.
Yeah,
You don't
I would
have
like to.
do the calculation right on the hot seat.
Can I ask the last two people to, they get one question and not have all the seats?
I just have one comment, which is quite simple, addressed to Eric. We're not seeking to have probabilities for individual histories of geometry, and certainly not solutions. We're looking to assign them to coarse grain sets, right? That is, which can be finite, and therefore I don't think we'll have the problem that you mentioned. But your point is very well taken about not understanding what we're doing, because we still don't have, in my opinion, a physically motivated method of coarse graining geometry, even in the classical theory. Thanks.
Thank you, Simon Saunders. Forgive me, Chairman, I'll just violate your rule because I have an announcement. And I have a question, so I think that's fair enough. So the announcement, there seems to be some confusion about what these roundtables are for. I'm sorry if that's the case. I thought I'd made it clear to both the present participants that it was to comment on the sessions that have gone on this morning and to come out with some comments of their own. If that isn't clear enough, then may I say it again for this afternoon. The roundtable is in order to comment on the sessions that have gone before this afternoon. And tomorrow morning, the roundtable is to comment on the sessions that go before tomorrow morning. Okay, good. And in the spirit of what a roundtable I think ought to be for, and my question isn't actually to the people on the roundtable, it's to Brad Pitts, because it's the session that went before that we're talking about as well. Just a question about these localized energies. One of the remarkable things about GR is that gravitational energy is not localized, and correspondingly, there's no question that there's a link, although it's an intricate one, and perhaps Bob will be the person to explain it better than me. The gravitational energy doesn't enter on the right-hand side of the field equations. Okay, but now, it's sort of slightly worrying, Brian, if you have now local gravitational energy, then why should that not behave as any other local energy? Why shouldn't it gravitate, and why should it not enter on the right-hand side of the field equations?
Well, I think it's...
Yeah. Brian, can you give me a one-sentence answer?
Sure, it does. It does fit on the right side if you want it there, and Einstein and Zentworf haltingly, and particle physicists more seriously derive Einstein's equations that way. Basically, it's the nonlinearity of Einstein's equations. Now, there are issues of field redefinitions and things along those lines that make it tricky, but basically, it is on the right side if you want it to be. Look at, say, Achille Papapetrau's work.
You transfer part of G mu nu over onto the right-hand side. So you get this truncated G mu nu, which sort of looks like an Einstein field equation is equal now to a nonlinear part of G mu nu plus the T mu nu. And that whole thing is now ordinarily conserved just with ordinary derivatives rather than covariant derivatives.
Yeah, I understand that part, but what about these local energies, this infinite collection of local energies that Brian was introducing? Do those figure on the right-hand side too?
That's what they are, yes.
This is another way of redescribing what...
Yeah.
But it is important to note that but it is important to note that you now have pseudotensor equals tensor plus pseudotensor, which to me just makes no sense.
Okay, on that note, the organisers have asked me just to note quickly that the membership of the afternoon panel, which I think is incorrect on the original printout, so it's as given here, Jan Levin, Priya Natarajan, Klaus Beisbach, Pedro Ferreira. I think Khalil Chamchan also has an announcement to make, but first could we please thank the roundtable members again.